welcome to the NPTEL online certification course on microelectronics, devices and circuits. This module we will be taking care of a small signal circuit model for BJT. The obvious question asked is why should we require this? Well, BJT as a standalone device has got no usage or application. So, this has to be integrated onto a circuit. So, for example, BJT is an amplifier, BJT as a switch, BJT as a current source and so on and so forth. Therefore, if we have understood how a BJT works, which we have already done in our previous interactions, we will understand or we will together learn how this BJT the device can be broken down into sets of active and passive elements, so that it is very easily integrated with the circuit analysis, and it is easier with circuits, and it is easy to do the analysis in circuits in a much detailed manner. Why small signal? We will discuss why small signal now. What is the meaning of small signal? Let me first make it clear to you. A small signal primarily means that the Q point does an excursion of approximately plus minus 10% from its quiescent value, right. So, if you have biased your device, then we define this to be as a small signal, right. So if you have biased your device say at 1 volt VCE, right, 1 volt, then if the input signal changes it from 1.1 volt to 0.9 volt peak to peak, I would expect to see that this to be as a, we can define this to be as a small signal. This is a rather not a very decent definition, but nonetheless works fine for all circuit applications. Assuming that this much amount of variation in the voltage, input voltage will not force the device to go into either the saturation or cutoff region. So, if you have biased your Q somewhere in the middle of active region, a 10% high rise or fall will result in approximately a linear change in the value of your amplification, right. So, here is still in the linear region of amplification as far as Q point is concerned. So, two things: one is a small signal circuit model primarily means that I am assuming that my input signal is basically small signal, which means that it is just plus minus 10% of its quiescent value. And the second point which I am assuming is that that there is no non-linearity into the picture by virtue of a large signal, right. So, and the third point is that obviously we require to have a corresponding circuit elements being inserted, so that whenever we plug this BJT and use it as a switch or any device, we can easily do that by doing small amount of manipulation in terms of circuit applications. So, let us see what the issues are. So, let me come to that point in a detailed manner. I will take one by one as we move along. If you see clearly, again this is, as you can see, this circuit is basically a BJT in a emitter grounded. So, this is basically your emitter grounded configuration, or even a common emitter configuration, or emitter grounded configuration, or common configuration. And what you see from here is that VBE is the applied AC bias which you are giving, and this VBE is the responsible for biasing it in the Q point, appropriate Q point. We define therefore IC, the output current IC, to be equals to GM times VBE. So, if you understand, VBE is the voltage which you have applied here, right, and this VBE is varying voltage, because that is what the input voltage is all about. So, one time it is 1 volt, 2 volt, 3 volt, then again comes to 2, 1, so on and so forth. So, it is a rising and falling, maybe a sine wave, maybe a pulse waveform, maybe any of the waveforms available to you, and therefore, this base to emitter voltage which you give, that converts into a corresponding current on the collector side. How? By mathematically multiplying with a value which is GM. GM is referred to as transconductance, right, and it is defined as del of, in this case del IC del VBE, right. So, it is defined as rate of change of collector current with rate of base of voltage. So, once you get this to be as GM, right, I simply get del IC to be equals to GM times del VBE. So, higher the value of GM of a transistor, I would expect to see a larger amplification appearing to me, right, because higher the value of GM will primarily mean that the transistor is more sensitive to variations in the input voltage, right. So, GM is basically a notation or a parameter which gives me how sensitive your BJT is all about. So, if your BJT is quite sensitive, I would expect to see a large value of transconductance available to me. So, I define GM to be GM is equals to IC by VBE. So, if you see it is IC by VBE and this is replaced by VT for the lowest case, because this is the thermal energy which you get, which is 25 millivolts at 300 Kelvin, right. We can also write down therefore GM to be equals to del IC del VBE for a fixed value of IC, right. So, at a fixed value of IC, what is the change in this thing, but you need not forget about all these things, you just forget GM is basically del IC del VBE, which you see, right. Now, if you plot IC versus VBE, this versus this, let us see why and how we get IC versus VBE in the next graph. So, for a common emitter configuration, if you plot say VBE, right, and if you plot say maybe an IB, let us suppose, right, let us see how you plot IB. Now, if you plot IB, it will look something like this, right. We have discussed this in our previous discussion. This is the threshold voltage or the knee voltage for the p-n junction diode, which is 0.7, right. So, for IB, if you have a common emitter configuration in this case, then this is the value of VBE, right, and when this VBE crosses 0.7, right, this fires this junction, switches on this p-n junction, and as a result the current starts to rise, right. Below that particular point, the current is very low or very smalls down very drastically. So, IB with VBE is in this manner. We have also seen from our previous discussion that if you bias your device in such a manner that your Q point is here. So, this is your active region. If you bias your device in the Q point here VCE, let us suppose, right, then I can safely say that for the same change in the value of IB, I would expect to see same change in the value of IC. So, remember when we are plotting the graphs, right, for various values of IB, when we are plotting IC versus VCE, right, with common emitter configuration for various values of IB. So, it is IB1, IB2, IB3. So, you see when, so this is IB1, this is IC1, this is IB2, IC2, this is IB3, IC3. So, this IB is of the order of few microamperes and this is of the order of few milliamperes. So, 1000 times increase is there approximately between base current, but please understand that for the same increase. So, if this is say IB2 is say 1 micron, this is 2 micron, let us suppose, then this current will be actually suppose 100 times is larger. So, I get 100 micrometer here or 0.1 milliampere and I get 200 microampere. So, you see for the same change in delta IB, right, I get the same change in delta IC. So, delta IB, right, and the delta IC, if you want to find out, the rate of changes are always the same. So, for the same increment in delta IB, I get equal increments in delta IC, right. The increment themselves might be different, obviously it is 100 times larger. So, quantitatively they are different, but I am 100% sure that if I increase the base current by once, my collector current will also increase by once. If I increase the base current twice, my collector current will also increase by twice. Why? Because I am in the linear region of operations, right, And therefore, what I wanted to tell you is that if this is IB versus VBE, exactly the same graph is for IC versus VCE. So, if you plot IC versus VBE, you will get the same curve again, right. Only thing will be that this IC will be in milliamperes, which was here, it was in microamperes or maybe milliamperes as well, but this will be more on milliampere, right. So, let me show you therefore, if you plot IC versus VBE here, and then if you input in the input side, if you vary, this is your input curve, VBE is varying, it is a triangular waveform which you have given. This triangular waveform, again small signal assuming, so that the Q is just shifting from this side and coming to this side. So, the maximum value is Q is this and this. So, we are still in the linear region of operation of the transistor. I get this to be the output, right, this to be the output, triangular output waveform will be there, right. Now, the slope of this curve, which you see, this curve, the slope of this curve, right, which is del IC del VBE, this is basically your GM, transconductance. So, if this slope is much steeper, I would expect to see a much larger variation in the output waveform for the same change in the value of input waveform, fine. So, that is the small signal model, and so in the small signal model, therefore, we will learn one important point, and that important characteristics is transconductance GM, and GM is therefore defined as the transconductance, in which in this case happens to be del IC del VBE, right, and it gives me an idea about sensitivity. So, if I know the base to emitter voltage, I can predict the value of the collector current directly by multiplying GM with the rate of VBE, right, and that is quite an interesting phenomena which is there with us. Now, we define another resistance known as the small signal input resistance, and it is referred to as R pi, right, and it is nothing but the resistance looking from the base side, where between base and emitter, right. So, looking from the base side, if you are looking from the base side, the resistance offered by this is basically VBE by IB. So, VBE is the voltage which you see between these 2 points, and IB is the current by virtue of this voltage. So, VBE by IB is equals to R pi, right, R pi. So, it is basically the forward biased on resistance of a BJT, right. It is an on resistance, which means that the base emitter junction is forward biased, it is getting on, and therefore, the resistance offered is defined as R pi, right. But please understand, this you are looking from the base side, right. So, you are looking from this base side and you are trying to find out. So, your emitter is grounded, please understand. Another is RE, which is basically the base to emitter resistance looking from emitter side. So, you give a potential on the emitter side and you ground the base side, and then looking at that you will get the value of RE to be equals to VBE by IE. So, it is VBE by IE, right. Obviously, as you can find out, IE is much larger as compared to IB. So, I would expect to see RE to be much larger, much smaller as compared to R pi. So, R pi will be relatively larger as compared to RE. Fine. So, I get R pi is equals to therefore VBE by IB. This is also equals to VBE by IE, RE, right. So, R pi can be written as VB. So, what we can write down is that it is equals to beta by GM, right. How beta by GM we will just show it to you. If you remember, GM was how, what was the definition, was del IC by del VBE, right. So, if you put del IC by del VBE here, so I get what? So, I get, if you put, so I get beta divided by del IC by del VBE. So, this VBE goes to the numerator, I get del VBE at the top, right, divided by into beta divided by del IC. This you get, right, this you get. So, this VBE is coming from here. So, you see, now you see, remember the definition of beta from my previous discussion was beta was equal to was equals to IC by IE, remember, right, IC by IB, sorry, IC by IB, right. So, if you put IC by IB here, I get IC, so I can replace beta and make it IC by IB, right. This IC gets cancelled out, I get VBE by IB, right. So, this is equals to R pi. So, R pi equals to beta by GM also we can write down. So, I will do the definite, I will do it once again if you want to. R pi is given as VBE by IB, remember. So, we also know R pi has been also given as beta by GM. We know GM to be equals to what? GM to be equals to del IC del VBE. So, if you put the value of GM, I get R pi. If you place it this equation here, I get beta times del VBE divided by del IC, right. Now, we know the definition of beta as the current gain in common base configuration, and therefore, I can write beta to be equals to IC by IB. So, del IC del IB, let me write down. Place this value of beta here, and therefore, this del IC and del IC gets cancelled out. I am left with del VBE upon del IB, right, and that is what we are getting here, fine. Since it is a small signal, therefore, del VBE equals to VBE and del IB equals to IB, and therefore, this is valid assumption which we get. So, I get beta by GM as the R pi value, fine. So, beta is relatively very high values, and therefore, R pi will be very high. So, this is what we get from our discussion as far as this is there. Similarly, RE therefore, can be written as IE is the emitter current and VT is the base to emitter voltage at 300 millivolt, we will write as VT, thermal equivalent voltage. Therefore, I can write down that R pi could be written as beta plus 1 RE, right, and you can do it yourself to find out this value. That means approximately R pi is approximately beta times larger as compared to RE, right. So, which means that and it is expected also, if you look very carefully, the reason being that the base is, so looking from the base side, the resistance is very large as compared to looking from the emitter side, and you can understand why is it, because base has got relatively low doping, right, and the area is also very small. So, in both will result in very high resistivity, or resistance will be typically very high, and that is the reason R pi is much larger than beta RE, approximately 100 to 200 times larger, right, and that is the reason why you get it. Therefore, R pi can also be written as VT by IB in case you want to do it, and RE can be written as 1 by GM as well, assuming that beta is approximately equals to 1. I can get to be approximately these approximations can be taken care of or can be handled easily. So, we have understood therefore that for small signal model, if you are looking at the base side emitter side, the resistances are not equal. From the base side, resistance is much higher as compared to that from the emitter side. We come to the models, various models of BJT which is available, small signal models, these are again small signal models, these are all small signal models which is available, right, and they are quite interesting and very easy to handle from circuit point of view once we know the basic fundamental principles of working of these devices. Look at, so we have already learned that BJT is basically a 3 terminal device, that everybody knows that BJT is obviously a 3 terminal device. So, what are those 3 terminals? Base, collector and emitter, right. So, the arrowhead which you see, the blue arrow here, blue arrow here, blue arrow here shows you the direction of the conventional current, right, and therefore, we say that looking from the base side, the amount of resistance offered is R pi, and across it we have a VBE as the voltage drop available to me. So, therefore, IB can be directly written as VBE divided by R pi, right. VBE is always fixed, approximately 0.7 is suppose the approximately voltage. If I give you therefore the R pi value, you can predict the value of IB directly, right. Now, this is the therefore the base emitter junction, right. Let us look at the base collector junction. We have already discussed that base collector junction, the collector starts to behave like an ideal current source, right. So, it behaves as ideal current source. How much is the value of current? Will be given by GM times VBE. Remember, GM was equals to del IC del VBE. So, del IC del VBE, VBE multiplied by VBE, the VBE get cancelled out and I get the current available to me, right. So, this is the current source current source with me, and this is the direction. The direction of the arrowhead of the current source tells me that the current is directed inwards, which means that it's basically an NPN transistor, and therefore it is directed inwards, and therefore you see this directed inwards, whereas emitter current is directed outwards, right. So by my previous definition, we know that GM is equals to IC by VT, which is available here, and this is beta by GM is R pi, right. So it's completely analogous to C on the right hand side, this one, right. This is also a hybrid model, hybrid pi model. It looks like pi, so that is the reason it is a hybrid pi model. Moreover, it is made up of R pi, and therefore it is a pi model. So you remember R pi is the resistance offered by the base emitter junction, and therefore we have R pi as the resistance here. On the whereas on the collector side, it is a current source, wherein current source IC will be equals to beta times IB, right. So just if you have a large value of IB, I will get a large value of IC, and I can therefore have a constant current source towards the collector side, right. Therefore, this model will give you very first instance the input impedance and output impedance of the device, right. So if you look at a BJT, therefore the output impedance is basically the output impedance is Z out. If you want to find out, is looking from the collector side, if this is the output, how much amount of resistance is offered. Of course, you can see from the output side, if you look very carefully, it is being terminated across a constant current source, and therefore Z out will be approximately equal to infinity in an idealized condition. So if you want to follow a hybridized pi model, then Z out will be equals to infinity, and Z out will be infinity primarily, meaning the reason being that we are looking into the current source here, an ideal current source, right. And assuming to be an ideal current source, we are assuming that the Z out will be infinity, whereas looking from the input side, if you look, it is Z in, input impedance will be approximately equals to R pi, fine. If you are looking from the so this is for the common emitter configuration, right. I leave as an exercise for you to find out for common base and for common collector. Please do it, right. Please do the necessary, right, pi model for CB and CC, common base and common collector, right. In common base, you will see it will be RE which will be coming into picture as the input impedance, right, and therefore you should be able to handle this hybrid pi model in a much better manner in this case, right. And so this is one model. The second model, which is most prevalent, but most of the time you use a hybrid pi model for most practical purposes, but sometimes you also use what is known as a T model, right. This is a transmission model or T model which you see, this is the T model which is there, and the T model still again 3 terminal device, so base, collector and emitter. We have also seen that the resistance between emitter and base is RE, looking from the emitter side. Looking from the base side, it would have been here R pi, but since we are looking from emitter side at this case, we are giving RE. You can also have an R pi here, but they will be in parallel. So in parallel, it will be always less than the least, remember, and therefore this has been neglected. So you see R pi and RE will be in parallel. So since they will be in parallel, the maximum, the highest value will get neglected. So highest is nothing but R pi, and therefore R pi is not shown in this diagram, right. And please, so therefore understand that why R pi is not here or here, because it is so large that it does not play a major role, RE plays a major role. So I get RE here, the voltage across RE is basically my VBE, base to emitter voltage, and this is the applied voltage which you see. The current direction is of course the conventional current direction, as we have been discussing quite often, and therefore the collector current will be equals to GM times VBE, right. We have again discussed this point as the input point. So you see so what I am trying to tell you is that your base emitter junction or your base emitter voltage, right, VBE starts to change the value of your current flowing through collector, right, and that is basically therefore a controlled current source with you, right. So basically it is a current controlled current source, because IB will change the value of IC, and therefore it is basically known as a current controlled current source. So I get from here that it is alpha by GM is the value of RE which we get, alpha by GM. You can prove it yourself to get the value of Re. Alpha is basically the common emitter current gain, right. Common emitter current gain will mean that you will have Re approximately equals to alpha by Gm, right, and you can get the value of alpha and Gm low. It's typically very low because alpha will be hardly of the order of 0.99 or 0.98, and this Gm will be typically large because sensitivity is very large. So your Re will be typically very small quantity. So your resistance looking from the emitter side will be very small, right, and that makes it go to a very small state or a very small region. And therefore, as you can see on the right hand side, if you look very carefully from the common base configuration, I get Re, I get alpha times IE as the collector current, and therefore for a common emitter configuration, for this is common emitter configuration CE, this is for the CB configuration, and therefore I can get the value of this thing. So I will recommend that for both hybrid pi model as well as T model, for all the 3 configurations CB, CE and CC, which means common base, common collector and common emitter, please try to find out the value and the model itself, please try to get it from any standard books which are available in the market, right. Let me therefore now come to the basic, we will finish with this common emitter configuration. Let me come to the common emitter configuration now and explain to you what common emitter configuration, how it works as far as how we are inserting the small signal model in a common emitter configuration, right. So this is the application of the small signal model, right. So what is the application? The application is something like this, that I have a signal input resistance, I have a input signal, I have a BJT which is there, RC is the resistance. So if you look, Rin is basically, which is this one, is the input resistance looking from the base side, and output resistance looking from the collector side is Ro. So if so what we are doing, we will replace this. So if you look out of the blue box, this blue box out of look, this RC is this RC, so this RC is this RC, right. This R sig which you see is this R sig, right, signal. So from looking from this side, this can be broken down into an R pi, right, because R pi is already known to you, and this will be Gm times R pi, right, and R0 will be the output impedance offered by the device which is there for the device itself, not from the circuit point of view. So I therefore get R0 always parallel to my current source here, right, howsoever large or small we do not know, but it will be the value which will be there R0 here. So we get Rin to be equals to R pi, no need to understand why is it, very simple, because looking from this side, from the base side, I only get R pi as my impedance. So R pi is the Zin value. V0 is Gm times V pi, Gm times V pi, V pi is nothing but the voltage across this VBE or V pi, whatever you want to name it, is basically the output current, this multiplied by RC. So this RC and RO in parallel, right. So the effective resistance seen by the current is basically RC parallel to RO. If you multiply with IC, I will get V0, right, and I get V0 here. So R0 is nothing but RC parallel to R0. So the output impedance is basically RC parallel to R0, right. This is the output impedance which you see. So for a common emitter configuration, we were able to see the output impedance, right. Okay. With this knowledge or with this basic knowledge, we will stop here today, and what we have learned is basically the small signal input model for a BJT, and in the next turn we will look into how we can apply further for the common base as well as common collector configuration design. So we have learned how to bias a device, DC bias, superimpose AC signal over it, and we have also learned how to use this for the purpose of common emitter configuration using the small signal model, right. I hope you have understood the issues taken up in this lecture. Thank you for your patient hearing.